Okay, so let's go ahead and get started. All right, hopefully y'all's exam went well. Did anybody have any questions about that they wanted to ask me before I went ahead and start? Okay, that's usually how it goes. But I saw where are the grades? I'm not 100% sure. They should be on Blackboard, but I don't usually have access to that. I don't have access to that, so I'm not really sure. That's kind of based on your professor and who you have. But Dr. Thompson, I did see his email to everyone saying like what y'all's averages looked like, which they were actually pretty decent compared to, they were actually really, really well compared to the rest of the exam grades. So I'm actually really happy about that. And y'all did a great job. So good job, pat yourself on the back. And then hopefully that means in this section, you're a little more prepared for the final. So that should feel kind of good. So how my sessions are going to go from here on out, because I only have 3 more, which is crazy, but and a little sad. But so what I'm going to be doing is today I'm going to be trying to do all of 11 and all of 12 that I think is the most important for the exam. Keep in mind, I usually don't have time to cover everything just because of time. We've got limited time. So whatever I cover in here isn't necessarily all that's going to be covered on the exam, but it's what I feel is the most important. So I still recommend looking at your PowerPoints that your professors give you, as well as looking through the textbook to fill in the gaps that I don't necessarily get to. Because I do think that going over test prep and practice exam problems is more important. So after Thanksgiving, I'll have 2 more sessions, one on the Monday of finals, or Monday starting of finals week, and then one on the Tuesday. And then those are my last sessions for this semester. And in those sessions, I know in the email it said that I was going to be covering chapter 12 in part of 1. That really only depends on if I can finish it today. But I still probably won't end up putting 12 on that packet just because I want to focus on review. So what I have actually done for y'all, I created like a full review packet that I'm going to be giving you at the beginning of my next session and the session following. That kind of just has everything condensed into one packet. It's quite long, but personally, I think it's really helpful. I actually started to make it when I was in the class myself, so I made it to help myself, and then I made some alterations once I started teaching, and yeah, I've been giving it out since then. So I'll give that to y'all. Of course, yeah, thank y'all for coming. I'm glad it helped. I'm glad. And then the rest of the days, I don't intend on doing a review. I intend on doing practice problems. So I don't really know what Creighton and Elliott, if they're going to do an actual review day, just because there's so much packed into this course, it's going to be hard to, fit an actual effective review day in here. So I've really just kind of selected some problems that I think most people have had problems with, or that Dr. Thompson have told me are important. And that's kind of how I'm going to design those packets. So we'll have 2 practice exam problems sessions. I'm losing my words, but I think that's good. So that's kind of what to look forward to. But let's go ahead and just jump right into chapter 11 and 12. They're very concept heavy. And so that's why I put a lot of, this is going to be a really wordy packet. I'm really sorry. It's before Thanksgiving, and I know y'all are probably tired and just want a break, but it will be concept heavy. So if you do have questions, just let me know. There aren't going to be very many practice examples or problems on this packet, just because there tend to be very few questions on the final exam over this material, but it's still good for you to know, okay? That being said, I'll probably have some problems in my next 2 sessions over at least some of these problems, okay? But I'm not really going to stress them too much. I just want y'all to know them. So let's get started. Now that I've talked y'all's ears off. Okay, so chapter 11.1, valence bond theory. Y'all can all see this okay, right? The screen? Okay, perfect. So valence bond theory and orbital hybridization. Okay, so orbital hybridization can be a little bit scary, a little bit complicated, but hopefully I'm gonna simplify it for y'all, make it a little bit easier to understand. So let's define it real fast. If you can't read my handwriting, I understand. This is my personal key and it's messy. I'm going to read it out to you, so you should be able to see that, but I can also type things out if you need it. But I'll read it and hopefully that'll clarify things. So valence bond theory, or abbreviated as VB, is a covalent bond forms when orbitals of two atoms overlap and a pair of electrons occupy the overlap region. So basically, we're just going even deeper into what a covalent bond or different types of bonding are, okay? So really what a covalent bond is, they're not stuck. It's just two overlaps. So you've got two atoms with orbitals of electrons. And when those orbitals overlap, the electrons stop going in a circular, if you think about it, in a circular pattern, in a circular cloud, and instead they accumulate into a region occupied by those. And that's the region we call a bond, okay? So when those two orbitals overlap, the electrons then are attracted to that region and overlap in that region, okay? And that's what valence bond theory is. We have some central themes of our valence bond theory. So let's go ahead and just start that. If y'all do need me to slow down at all, please just say so and I will. It's hard for me to gauge because usually on my packets, I'm writing it out with y'all. So it's kind of easy for me to gauge how fast I'm going, but when I'm doing this, it's a little harder. So let's talk about this first bullet point here. The first central theme is opposing spins, and we should already kind of be familiar with this idea because when we talk about orbitals, we want opposing spins in orbitals. And that same thing is going to be true when we're talking about valence bond theory, when we're talking about the region that these bonds are overlapping, or not the bonds, sorry, the orbitals overlapping. So we still want opposing spin. And as you can see, I kind of just drew a little bit of an example. This is 1s and 1s. I know that second one looks a little funky, but it's just two hydrogens with their overlapping regions. And I just showed you that in this orbital, each, the outside orbital of each hydrogen has one electron. And as you can see, this one over here has an up arrow and this one has a down arrow. That overlapping region has to have an up-down format as well. So, and just a little side note, electrons spend more time in the overlapped area of the orbitals, and they have opposing spins. That's just like a little side note. Like I said, they're attracted to this overlap region. They'll still go outside of it a little bit, but the most common area they'll be found will be in that region there, okay? So that's that first idea of valence bond theory, opposing spins, hopefully nothing new, but yeah, okay. So the second one, maximum overlap, okay? And we can imagine this, our compounds want to maximize their overlap because if you think about it, the more overlap you have, the more stronger that bond is, the stronger the grasp, and that increases stability. So that kind of has to go into a maximum overlap. So like I just said, the greater orbital overlap, the closer the nuclei are to the electrons, the stronger the bond. And that second line, that little in between the commas, the closer the nuclei are to the electrons is kind of important in just rationalizing it in your head. We know that our orbitals are filled with those negative electrons, right? And our nuclei are very positive, and when they're closer together, you have a neutralization of those charges, and it makes it more stable. So that's kind of how I rationalized it out in my head. So maximum overlap helps with stability for a couple of reasons, but really the main one being the closer the nuclei are together, the better they are at neutralizing those electrons. Okay, trying not to go too fast. And then the third one is hybridization. And this is the one that trips a lot of people up, and it tripped me up for a while too. So I totally understand where you're coming from if you right now think it's confusing or don't understand it completely, but we will figure it out together. So basically, this is the process of orbital mixing. So you guys should be relatively familiar with how to draw orbital diagrams. When you draw, the shell of 1s and then 2s and 2p and all that stuff. And then we distribute the electrons using Hund's rule and Aufbau's principle and all that stuff. Well, that's just looking at a single atom. And when we're talking about things in nature, we're usually talking about them in terms of molecules because atoms will bond to each other to form a stabilized form, which is a molecule, right? Those are going to be, almost everything is in terms of a molecule. So we can't really just look at, single atom orbital diagrams. We have to look at molecule orbital diagrams. And as you can imagine, putting multiple atoms together can get really complex when you're looking at those multiple orbital diagrams. So that's why we use hybridization, and we really just there's kind of a simple way of doing it and of visualizing it. It can look complicated, but I think once you start taking it apart, it's actually pretty straightforward. So we'll talk about it today. But valence orbitals in the isolated atoms become new orbitals in a new molecule, or in the molecule. And new atomic orbitals are called hybrid orbitals. I don't know. Oh, I hole punched it right there. So that should say orbitals. Let me just type that out so we can. I hole punched my key, and now you can't see what that word is. Okay, so really valence orbitals in the isolated atoms become new orbitals in the molecule. So remember, valence orbitals are the ones that we use in bonding and when in the isolated atoms, in just a single atom alone. However, when we put them in a molecule form, if we put multiple atoms together, we have to create new orbitals, otherwise known as hybrid orbitals, to actually allow those electrons to occupy the new bond. Okay, so we do have to do a little bit of manipulating. And like I just said, new atomic orbitals are called hybrid orbitals. Okay, so let's talk about some features of these hybrid orbitals. This is really important here, this first bullet. The number of hybrid orbitals form is the number of orbitals, or it's kind of messed up writing, but the number of hybrid orbitals formed is the number of orbitals mixed, the number of atomic orbitals mixed, okay? So if you mix 2 atomic orbitals, you'll have 2 hybrid formed, okay? And I'm gonna talk about this and actually demonstrate it for you. So if it doesn't make sense right now, it should in just a minute, okay? The type of hybrid orbital varies with types of orbitals mixed. So if you're mixing an s and a p orbital, that hybrid is going to be slightly different than if you're mixing an s orbital and another s orbital, okay? So that's what that means. I'm going to talk about it a little bit, but really it's just the type of orbital varies, okay? And then the shape and orientation of a hybrid orbital is to maximize its overlap with the orbital of another atom. So again, it's just back to the same concept. We are going to try and maximize overlap between the orbitals so that we can be stable, okay? So I have listed for y'all below here are types of hybridization and what they kind of look like. Obviously, you're not going to have to necessarily memorize these images here because they are very complex and there's a lot going on in them, but I think it's still good to kind of see what this is talking about. So it's up here, it tells you the atomic orbitals that you're using. So if you're using just a single s orbital and a single p orbital, when you mix them together, you're going to get 2 sp orbitals. So as you can see here, you're using 2 different types of, so it goes back to this rule up here. Number of hybrid orbitals formed is equal to the number of atomic orbitals mixed. Here we're mixing an s atomic orbital and a p atomic orbital. So that's 2, right? We're mixing 2 orbitals. And as you can see down here, we're forming 2 hybrid orbitals. So that number should relate. Now here you're mixing 2 and 1. So that's going to be 3. You should also have 3 right here. So you should see this pattern always, okay? Something else you should also recognize is that it's going to follow the same formula or a very similar formula as when you're doing your electron configuration, right? The only thing it's not including is the level, right? It doesn't say 1s or 2s2 and 2p2. It's just a single letter, okay? So for mixing 1s and 1p, we're really just going to just straightforward, it's going to be 1s and 1p. Okay, same thing goes for here. We're mixing 1s and 2p, 1s and 2p. And please note that once you hit this 3p, once you have hit 3 of them, remember, when we're talking about the p energy level, we can't have more than 3 orbitals, right? And that's why we start using the d orbital. So once you have used 3 of these p orbitals, you have to then incorporate a d orbital and so on. And the d ones can go on for a while because you have quite a few of them, okay? So hopefully you kind of see the pattern here. I'm going to break it down a little more, but really it's just kind of important to see that the number of hybrid orbitals you're forming is the same number as the orbitals you're mixing. If you've mixed 2, you're going to have 2 hybrid. If you've mixed 3, you'll have 3 hybrid, okay? All right. All right, are we good with this page? Do I need to go back up so you can copy anything else down, or do you want me to reread a sentence that is poorly written? Okay. Anybody else? Hopefully we're okay. All right. I can always come back at the end too if y'all need it. Okay, so let's go ahead and talk about this generalization. I just said it again. It's kind of has to do with this first little bullet point here underneath features of hybrid orbitals. But the generalization really is the number of electron groups determines the hybridization. If you have 2 electron groups, and we're talking about electron groups in your molecular structure. So if you're a tetrahedral, you'll have 4 electron groups. Okay, that's kind of what I mean here. So the number of your electron groups determines the hybridization. If you have 2 groups, it's going to be an SP, right? 1s and 1p. If you have 3 groups, it's going to be sp2. It's going to be 1s and 2p, which means 3. 4 groups, so on and so forth. So again, it's the same. It's very similar to the rule I just mentioned up above, but now we're just talking about it in terms of electron groups, which actually tends to help people because on the exam, they're going to give you a structure you should be familiar with, right? So maybe they give you, I don't know, maybe they give you like, let's see, a carbon surrounded by 3 or 4 chlorines. Okay, so that's a tetrahedral. It's kind of the same thing I just said a minute ago. But they'll ask you the hybridization of that molecule, and all you'll have to do is count those electron groups. And because it has 4 electron groups, it's a tetrahedral, right? It has 4 electron groups, meaning it should fall into the sp3 hybridization. Okay. Hopefully that kind of makes sense. But again, like I said, I'll have some practice problems on this in my next packets. Okay, so I am going to go ahead and scroll down. There's a big gap here because I kind of merged my keys. So if you need to see that again in a minute, we can come back to it. But we're going to be down here now. Okay, so that was 11.1. Now let's go ahead and talk about 11.2. So modes of orbital overlap and the types of covalent bonds. Okay, so orbitals can overlap by 2 modes, which give rise to 2 types of covalent bonds, okay? And here I used my dumbbell type bonding, which is my p orbital bonding, right? But it's not, it can apply to a lot of different types of orbitals, but this is the best one to demonstrate the idea that I was trying to get across. So it's not limited to this, but it's just a good example, okay? So end to end, for me, it's really easy to see in the p orbital because you've got one end and second end, right? That's end to end. And this is the overlap here. And then you have side to side, okay? Which again, it was really easy for me to visualize it in the not in the pi, sorry, in the p orbital because it's pretty easy to see it. You know, it's pretty clean. So side to side is kind of in this. So it looks like there's 2 regions of overlap in a side to side, okay? So those are just 2 types of overlap, and we'll talk about them a little bit more. So let's just talk about sigma. So we have 2 different types of overlap, and accordingly, we also have two different types of bonds, okay? Sigma and pi. So this first one, again, this little symbol, it looks like an O with a little loop here. Sigma bond, as you can see, I kind of drew out to the side a good example of what a sigma bond would be. In other words, there's always going to be a sigma bond. In every bond that you have, there will always be 1 sigma bond, okay? So if you only have 1 bond, this bond here will be labeled as a sigma bond, okay? And then later on, we'll see that in the triple bonds and double bonds and all those types, there's always going to be at least 1 sigma bond, and the rest of the bonds will be labeled as something else. And I'll talk about that in just a second. But a sigma bond is formed by end-to-end overlap or orbitals. So it's going to form in this manner, okay? And you'll always have 1 that forms in an end-to-end overlap, okay? Another key factor about it is sigma bond has its highest electron density along the bond axis, which actually kind of makes sense because if you imagine this overlap as a straight line as your bond, right? If you see this here, if you put the central of 1 carbon here and the carbon here, it's going to kind of look like this. If you put the little, the overlap there is going to represent your bond, and it's going to look like a line. Whereas here, if you look at side to side, you can see that there's overlap in 2 regions, which is kind of above the bond, which if you imagine the bond is going straight to the middle here, it's above the bond and below the bond. So when I'm talking about sigma bond, its highest electron density is along the bond axis, which goes straight through the middle here, okay? And that's what I kind of mean. And if you think about it also, if you think about it rationally, it also makes it look stronger, right? So that's something you need to know about sigma bonds. all single bonds are sigma bonds. That's just a rule of thumb. And sigma bonds do tend to be stronger. I think I have it written down below my key somewhere. But if not, you can just add that little note in here. But I believe I have it on here somewhere. So, okay, now let's talk about the other type of bond, pi bond. So a pi bond is formed by side-to-side overlap. So like I said, it's this one here, side to side. And it has two regions of electron density, which is also pretty visible in this example up here, right? You have one overlap right here and one overlap here. Okay. Now let's talk about where these pi bonds are located. And I usually like to throw some text in here so we can see it. So if we're looking at the bonds that are in this it's a double bond. I don't know why the shadow's there, but it is a double bond. So carbon double bonded to a carbon. The first bond, I mean, it doesn't really matter which one. It could be the top one or the bottom one. It's not that specific. But at least one of the bonds we know has to be a sigma bond. Because, like we said, there's always going to be a sigma bond in a group of atoms, okay? Always. The other bond is not sigma. The other bond is going to be a pi. Okay, so the other one is going to be labeled as pi. And we can do the same thing for this set of three down here. There's always going to be one sigma, right? But the other two, they're not sigma. They'll be pi. So we should have, I'm just going to write 2 pi because the other two bonds here are both pi bonds. Okay, and this is how it's going to be for every single set of bonds that we look at, okay? So, like I said, double bond consists of one sigma bond and one pi bond. A triple bond consists of one sigma bond and 2 pi bonds, and so on. No. So will there ever be 2 sigma and 1 pi? There will not. So the reason really is, if you want to think about it, I like to visualize this center bond as my sigma bond and my upper and lower ones as my pi bonds, and it kind of gives me an idea of this here. It looks like my bond goes straight through the middle, and my regions of like electron density that aren't sigma are kind of on the outside, kind of out here. But really the straight up answer is no, there's not going to be any other variation. There will always only be one sigma and then 1 or 2 pi or no pi at all. Okay. Any other questions? That was a good question. Okay. So that's that for that page. Does anyone want me to stay on this one a little longer? Okay, so let's go ahead and move on. This is a little bit I said about the strength. So because orbitals overlap less side to side than they do end to end, a pi bond is weaker than a sigma bond. So sigma bonds are really strong. And here's kind of where I tend to see the majority of people's questions about this concept is, well, we've been taught that triple bonds and double bonds are exceptionally strong compared to single bonds, right? So if this doesn't make very much sense, if sigma bonds are super strong, why are they weaker than double and triple? Well, the answer to this is, and the best, I can't remember who taught me this. I think it may have been my SI leader, but they were like, if you put a bundle of sticks together, it's easier to break a single stick than break a whole bunch of sticks in a bunch, right? You can easily snap a stick alone, and that's why it's weak. But as soon as you start building up multiple bonds or putting up multiple sticks, it's really hard to break all of them at one time. So it works in a similar manner. A bunch of skinny sticks put together can still be really hard to break compared to a slightly thicker stick alone. But really the idea is it's just the type. So if you look here, a sigma bond alone will be relatively easy to break, but as soon as you start pairing it with other bonds like pi bonds, it can get stronger together. But if we compare just a single sigma bond and a single pi bond, sigma is stronger than pi, okay, alone, if we're comparing them separately. So I would consider sigma bonds to be the thicker stick and then pi bonds to be the skinny sticks. And when you pair them all together, it's hard to break it just in general, okay? So that's kind of just the reasoning behind this and why it makes sense. But really, the reasoning behind why pi bonds are so weak is because they are side to side, and end to end is stronger because there's more overlap. Okay, so however you want to think about it, just remember that relationship there. Okay. All right. So let's talk a little bit about rotation. The type of overlap also affects the rotation about the bond. Sigma bond, because it's just a single bond, it allows free rotation. So those atoms can rotate in whatever direction they want because they're only connected in one place. But pi bonds, because it means you have 2 or 3 bonds, all of a sudden you're connected in 2 places and they can't rotate in opposite directions. The atoms can't rotate in opposite directions. So pi bonds restrict rotation. Okay. Yeah, so you can only have free rotation about a single bond, and that single bond is just always going to be sigma. Okay. So that was 11.2. We can move on to 11.3 if everyone's okay with the material in 11.2. I haven't, because y'all's exams were slightly out of order, not out of order, but they covered different material from last semester. I don't know if this packet's going to go over time or if I'm going to not have enough to put on the packet, but even if I don't have enough, we'll probably just end early. That's if I get through it all. But I seem to be going kind of quick, so no questions? Okay, so let's go ahead and talk about MO theory. So we just talked about, up here, we talked about VB theory. So we have 2 different theories. We've got valence bond theory and then molecular orbital theory. Molecular orbital theory is a little harder to visualize, so we're going to talk about that here. So molecular orbitals show given energies and shapes that are occupied by the molecule's electrons. Okay? So given energies and shapes that are occupied by the molecule's electrons. So key distinctions between molecular orbital and valence bond theories. So VB pictures a molecule as a group of atoms bonded through overlapping of valence shells, atomic and or hybrid occupied by localized electrons. In other words, it's a picture of a whole group of atoms with bonds through localized electrons, which are easier to visualize because when we say that, oh yeah, the electrons are in a bond, it's really easy to visualize. When we start saying, oh, they're in a cloud that's kind of near each other, or it's kind of shaped like this, it's a lot harder to visualize because it's not quite as solidified as the idea of a single bond, right? So valence just shows you bonds, basically, through distinct overlapping valence shell atomics and or hybrid orbitals. By localized electrons, well, as you can imagine, if our valence bond is localized, molecular orbital is delocalized. And that's why they're harder to visualize. So molecular orbital pictures a molecule as a collection of nuclei with orbitals that extend over the whole molecule and are occupied by delocalized electrons. So molecular orbital is much more accurate. As we should know, bonds aren't necessarily real. They're just there to help our brains adjust to the concept of what a molecule is. And it's a very difficult thing to visualize. So it's really helpful, but it's not necessarily accurate. We need to be getting into this idea that our electrons are in clouds and they are fluid, they move, they're not stuck in one spot. Even if they're participating in what we call a bond, they still can move outside of the bond's region. It really is just the fact that these electrons they're attracted to the orbitals. to the orbitals, the overlapped region. They're attracted to that area. So the reason we say it's a bond is because they're going to be found in that region relatively often. They'll be there frequently, but nothing's keeping them there. So they'll move out and they'll come back. So that's really kind of what delocalized means when I'm using the word delocalized. My next blank really is just, they're harder to visualize and we'll show you why. But let's talk about the formation of an MO and how we actually form a molecular orbital. So we add or subtract atomic orbitals of nearby atoms to form MOs. So this is where I'm going to start talking about the diagram, the combined molecular diagram, where you combine two single orbital diagrams will create a molecular diagram. So atomic orbitals is AOs. So if you need to know what that means, AOs, atomic orbitals overlap in two ways. You've got bonding MO, which is basically adding, okay? And then you have anti-bonding MO, which is subtracting. I used to have a image drawn here, but it turned out it was a little more complicated than I was hoping it would be. So I took it out so that it wouldn't confuse you. I'm going to still explain what these are, but just not using the image that I had already had on my key. So don't worry about the space there. But really just know that bonding MO is adding and anti-bonding MO is subtracting. And then we will talk about what they look like here in just a second. So bonding and anti-bonding have different shapes and energy. So bonding MO are lower in energy than the atomic orbitals that form it. So how I want y'all to be thinking about this is I'm just going to draw a hypothetical. So I don't want you to think that this is the actual, I'm going to draw it here. I don't want you to think this is like the only way you can see it. Oh, yeah. I'll wait just a second before I move on. Is this far enough up? Okay. Okay, perfect. So back to this sentence here, lower in energy than the atomic orbitals that form it. So if we're just talking about a simple s orbital, okay, we know what an s orbital is. Oh, of course. Hold on. Let me make this. There we go. Okay, so this is our s orbital, right? And say we're just combining two s orbitals. All right, I know those are really crooked, but it's fine. And I'll go ahead and label them so we don't forget. Let's just make it simple, and they're both 1s orbitals, okay? Now, if we were just doing these 1s orbitals without just like alone, if we were, say, hydrogen, if we were just drawing these 1s orbitals, it would be pretty simple for us because we know how to draw just a single atom orbital diagram, right? We know that there's in the 1s shell of hydrogen, there's only one electron, so we put an up arrow here. And it would be pretty straightforward, right? Well, now we're pairing this hydrogen with another hydrogen. So we have to figure out how to do this. And there's two ways. We can use bonding MO or we can use anti-bonding MO. And what this one is saying is bonding MO is lower in energy than the original atomic orbitals. So these two are the original atomic orbitals, right? Now, they're lower in energy. So would you expect it to be found if our energy is going in the up direction? Like this, would you expect me to put my bonding MO down here or up here? Lower or higher? Exactly, down, right? That's what my bonding is. So anytime you see a molecular diagram and a molecular orbital diagram, your bonding will always be lower. It'll always be down here because it's lower in energy. And if you think about it, we fill our lower energy orbitals first, right? We always fill those lower energy levels. So you're always going to fill your bonding MO first. And then if you can imagine, your next one, your anti-bonding MO is going to be higher in energy. So it's going to be found up here, except I keep drawing my line backwards. But so before I get ahead of myself, the electron density is spread between the nuclei, meaning we're going to take some electrons from here and we're going to take some electrons from here, and it's going to be spread between the nuclei. There's a nuclei here. And it's more stable. So bonding MO is more stable, okay? It's because it's more stable because it's lower in energy. And I want you to also be thinking about this whole concept that we are trying to bond to other atoms to become more stable, to become more energetically favorable, right? And if you think about it, we could just put numbers to it. Maybe right now the hydrogen atom is at 5 kilojoules of energy. I'm just making this number up. But as soon as it bonds to another hydrogen, it goes down to 1 kilojoule of energy, which is a lot more favorable. So that's what bonding does for every single atom we're talking about, is it lowers that energy physically. It's a really cool thought. So once you actually kind of wrap your head around it, by putting electrons into this lower bonding MO, we are physically making this molecule more stable, or these two atoms more stable. Okay. Antibonding is higher in energy than the AOs that form it. So as you can see here, we have one atomic orbital, another atomic orbital. The antibonding is higher in energy. Okay. I look at antibonding as a backup orbital. Okay. So if we fill this orbital, then we still have electrons, then we'll have to put them in the antibonding. But yeah. Okay. And then electron density outside the internuclear region. Basically, these are going to be, if you want to go back to thinking about it in terms of like a bond, the electrons that are found in the region on the bond, right, directly between the two atoms, that's going to be the ones here. They're going to be on the inside of that bond. However, if you have some leftover electrons that need to bond still, they'll be found on the outside of that main region. Okay, so they're easier to break, they're less stable, they're going to be outside the internuclear region. So the way I think about it is if I scroll back up, if I look at these bonds here, this central bond, this middle bond is technically in the internuclear region. And then these outer bonds, the ones on the outside, are on the outside the internuclear region. They're on the outside, they're my pi bonds, they're more easily broken, they're not as stable, they're my excess electrons that couldn't fit into the bonding region. They had to be in the antibonding. That's how I think about it. Let me go back down here. Okay, so that's the general idea of bonding and antibonding. Does that kind of make sense to y'all? Hopefully. Kind of? Okay. So do y'all have any questions about what it is? Anything that I can answer? No questions yet. Okay, well, it is a lot of info. Yes, I have two pictures that I'm going to use to kind of use as an example. So I'll do that in just a second. Yeah, like I just said, I've got a picture that I'm going to use and we're going to do that together. Okay, so let's go ahead and I'm going to talk about this next section here and then I'll pull up my pictures and we will talk about it a little bit more, okay? So electrons in molecular orbitals. So filling molecular orbitals with electrons. So MOs are filled according to Aufbau's principle in order of increasing energy, just like I said. So you're going to fill these lower energy levels first before you fill your higher energy levels. So that should not be familiar. That should not be old or like unknown information. That should be familiar to y'all. Ignore this show textbook page thing here. That was just a note for myself. And it wasn't a textbook page. I was going to find an actual problem for y'all. But MO energy level diagrams are in a diamond shape, and it's this shape here. So as you can see, we kind of form a diamond, and this is where I'm going to actually share my new page with y'all. So give me just a second. And I'm going to actually, I should have stayed on here a little bit longer and made sure everyone can copy it down. So go ahead and make sure you have it copied down. When y'all have it copied down, let me know. I'm good to go, and then I'll change the picture, okay? I don't want to go too quickly. Okay, sweet. And if I do need to come back, I will, but I'm going to go ahead and change my screen now. So let's go ahead and look at this one. Give me 2 seconds and I'll share it with y'all. Okay, so I'm going to blow it up a little bit. Can y'all see this okay? I can't even see my chat. Hold on. Okay, so real quickly, I want y'all to pay attention to a couple things, and I'm going to block out, I'm going to use this little thing and I'm going to edit this real fast. So real quickly, all I want you to focus on is this first energy level, right? Ignore what this little circle is underneath here. But really, if you were going to draw, and ignore the 2 here, if you were just going to draw a single orbital diagram or energy diagram for hydrogen, it would just look like this, correct? You would be in the 1s level with a single up arrow, right? Okay. So let's say we have 2 hydrogen atoms. So I'm going to draw them separately, okay? I'm going to draw one on this side and one on this side over here, and that's what this one provides me. So real quickly, I'm going to shorten out this little thing and just show my two hydrogens, okay? I'm putting them next to each other. I'm not doing anything fancy yet. I'm going to draw one of my hydrogen orbital diagrams here, and I'm going to draw the other one right next to it, okay? I haven't formed a bond yet. I haven't done anything. I just have my hydrogens sitting next to each other. Are we all okay with that idea? Okay, so this is the simplest way to do it. If you are given a problem like this, you're going to look at the 2 things bonded together, and you are really just going to draw their outer valence shell next to each other, okay? Just draw the valence shell next to each other. So we know that hydrogen's valence shell is 1s and 1s. So now I have to think, well, if I've got these 2 bonds or 2 atoms apart from each other, what does it look like when I bond them together? So the first question I need to ask myself is, how many electrons do I have that are available to bond? How many is that? Exactly, put together. I have 1 hydrogen electron, and then I have a second hydrogen electron over here. So that means I have two electrons that can form a bond. So I'm going to borrow them, and I am going to take them, and I'm going to place them in bonding and anti-bonding orbitals, because anti-bonding and bonding orbitals, those are the orbitals that form a bond. So if I just have my electrons here and here, they're not in a bond yet. They're 2 separate orbital diagrams. So in order to combine them into a single orbital diagram, I need to create new hybrid orbitals. Does that make sense? So anti-bonding and bonding are my new hybrid orbitals. Well, I only have 2 electrons to work with, so I have to start, now y'all tell me this, we talked about it just a second ago, I have to start with anti-bonding or bonding orbitals. Which ones do I fill first? Bonding, right? Bonding, because it's lower in energy. So I'm going to go ahead and draw my bonding orbital. I only have 2 electrons to work with. How many electrons go in every orbital? 2. So I should have both of these electrons placed here. I like to, these electrons here we steal them and we borrow them, okay? We bring each electron down. Now you can, in this case, see how one's an up arrow, one's a down arrow. You can change the direction. So yes, this electron here is a 1s arrow here, but when you pull it down, you'll just flip it around and make it a negative, because remember, we can't have 2 up arrows. It's just changing the spin, okay? So it's nothing too complex of an idea. It's okay for you to do that. Just remember when you're filling this orbital, and you need to change the spin. So here's just one more thing to recognize. You don't have 4 electrons here. What I like to think what this dotted line means is I'm taking some electrons from this shell and I'm bringing them down and putting in my new orbital, okay? I'm taking some of these electrons and I'm bringing them down and putting it in my new orbital. So it's sharing them, okay? So if I cover this up again, this is what it looks like when they're separated. When I create this second one right here, this new one, that's what they look like when they're bonded, okay? So this is where they're forming. Does that make sense to everybody? So this new orbital is my new bond. I have just created a bond between these 2 things. I have used the electrons provided in each of the atoms alone, and I've pulled them in and created a shared bond between the 2 atoms, okay? Now, in this case, do we have any more electrons, or have I used them all in my first energy level? I've used them all, right? So as you can imagine, if I go ahead and get rid of this box, I don't have anything up here. I don't have anything in my anti-bonding energy level because I've used them all, right? So I only have a sigma bond, not a sigma star. Sigma star here represents anti-bonding, and a single sigma like this without the star means bonding, okay? It's just a different way of labeling them. So if you see sigma star, remember that it's anti-bonding. If you see just a plain sigma, that's also just another way of saying bonding, okay? All right, so that's just the basics example for hydrogen, okay? I'm gonna try helium real fast so that y'all can see what I mean by if I'm doing helium, which is just one electron different. So I'm gonna go ahead and stop sharing this one. And I am going to share my other one. Give me just a second. Okay, so can you see this one okay? Okay, perfect. So do pi bonds have more or less energy than sigma bonds? Yeah, so you would say that pi bonds, they do have more energy, they're more unstable. They're gonna have a higher energy, yeah. Okay, so let's go ahead and fill this in. So as you can see, we have the hydrogen filled in, right? So with hydrogen, we only have one arrow or one electron in each of the orbitals, right? This is one hydrogen atom, and this is another hydrogen atom. Okay, well, let's do helium. So how many valence electrons does helium have in its exactly, we have 4 total, right? Helium, in each individual helium atom, we have 2 electrons. However, when we say we have 2 helium, we have a helium here and a helium here. We're going to have 4 total, right? Okay. So hypothetically, I know helium's not really going to oftentimes bond to itself, doesn't really need to, it's satisfied with its 2, but just hypothetically, we're going to do this one, okay? And I'm just going to say that we're going to have 2 heliums bonding to each other. Not very likely, but you know what? We're going to go with it. So, sorry, hold on. So I just have to make sure I fill this out all the way, and tell myself that for a helium atom, I have 2 electrons in one helium and 2 electrons in another, giving me a total of 4 electrons, right? So if we go by Aufbau's principle, we need to fill the lower energy levels first, right? Which means we need to put 2 electrons in my lower energy level, which is bonding. So I'm going to steal 1 electron from here and put it here. And I know that kind of just made no sense, and I'll pull 1 electron from here and put it in there. So now I have 2 electrons I haven't used yet, right? So where do I put those 2 electrons? Anti-bonding, right? They go up here. So I'm going to put 1 here and 1 here. Okay. Now, to make sure you've done it correctly, you need to make sure you look and see, well, I have 4 total electrons that were available for bonding, and now I've put them completely in the middle, meaning I have all 4 accounted for in my actual bond. Okay. So, all right. So that's kind of the explanation for why, if you did this for helium. I know helium wouldn't typically bond to itself, which is a little bit weird, but what if there's electrons left over? Then you'll have to create another energy level for them. But for this purpose, there won't be, because we're just bonding with the s orbitals. And when you do it with the p, there's a lot more space. So, and I can do an example with that in my next session. Yeah, I'll have to do it in my next session just because I didn't have that one specifically prepared. But I will definitely have an example of how to use the P1 for sure. Okay, so does this, I know it's kind of a complex idea, but does it kind of make sense? How we're taking electrons from atoms and then we're putting them in the middle and actually sharing them between atoms? Okay. And I mean, I know it's kind of a stressful topic just because it's so abstract, but in the past, they haven't had a crazy amount of problems on these, just because it's a cumulative exam, right? You have to know everything from the full semester. So they do have a good handful of these problems, but it's not overwhelming. So hypothetically, yeah, it would be a single, as soon as you fill this, okay, this gets hard because it starts talking about within s orbitals you can only allow single bonds, but as soon as you start going into the p orbitals you get double bonds. Okay, so for this case it would be a single bond, but when you go into the p orbital it becomes double bond. Okay, all right, so I'm going to go ahead and go back to my packet. Get rid of this and pull up my chat real fast so I can see everyone. So the antibonding always exists, but it's not always filled. And that's why I kind of said it's like a backup. If you have extra electrons, you throw them in the antibonding. But if you don't, then the antibonding doesn't necessarily need to be filled. Okay? It's like kind of just like a place to put extra electrons. And it'll be on the outside. It'll be less stable. It'll be more energy. It'll have more energy. So it does always exist, but it's not always filled. Okay. So let's talk a little bit more about electron configuration. So if they do ever talk about electron configuration on the exam, it's written as usual, except for the addition of the bond type. So if you're writing the type for H2, here's how it's going to be written. You're going to write where the electrons fall. So we know that they fell in the sigma, right? You have two options. You have sigma or sigma star. And we know that for just hydrogen, both of those electrons fell in the sigma bond, or in other words, they fell into the bonding MO, right? So you'll draw that first. So I have both of them fall into the sigma. It's in the 1s orbital, right? Because that's all we're taking them from. Both hydrogens, their outer valence shell are 1s. So it's going to be, they're in the 1s orbital, and then you do parentheses and you throw a 2 up there, and that says there are 2 electrons. Okay? So we have 2 electrons in the sigma 1s bonding orbital, meaning we have 2 electrons in the 1s bonding orbital, not antibonding. And if hypothetically, if there were electrons in your antibonding, you would follow it with parentheses sigma star, also in the 1s, because if we did helium, for example, helium had electrons in the sigma, or the bonding orbital, but it also had electrons in the antibonding. So we would draw another parentheses, we'd have sigma star, and then we would say 1s, close parentheses, both electrons were present, so we put a 2 on the outside as well. So you kind of just build on based on what energy levels you see, in the same way as you would build on in regular electron configuration. Yes. So the exponent is the electrons and how many electrons you have. And then in here is just specifically where those electrons are located. Antibonding versus bonding. And it's always going to be the outermost energy levels. So they're rarely going to ask you to put like a whole chain of these. If your atom is in the 2s energy level, you're not going to have to show the 1s. You're just going to show the 2s. Okay, so it's only going to be a couple of these long, usually 1 or 2. Okay, and it's really only going to apply to the outermost valence shell because it's all we really care about. Those are the ones that participate in bonding. Those are the ones that are important. Okay. All right. There's another way of doing bond order for this, and it really is just for predicting what will happen. So when we solve for bond order in regards to hybridization, we can use information we already know and predict how this atom will bond. So if you do bond order is equal to 1/2 times the number of electrons in bonding MOs minus the number of electrons in anti-bonding MOs, you'll get the bond order. And that'll predict about how your atom will bond, how your atoms will bond to each other. In doing so, if your bond order is greater than 0, your molecule is more stable and it will form. However, if your bond order is equal to 0, your molecule is stable as is, and the atom won't form because it has no reason to. So please remember when you're doing your molecular orbitals, it's really two atoms and determining if those atoms are stable or unstable. If the atoms are stable, why would they change their form? If they're stable, we're going to have to put energy into them to make them bond, and we don't want to do that. So the only reason they'll actually form is if they're unstable as is. So this is why it's helpful, because if our bond order is greater than 0, it means the molecule will be stable after it forms, so it will want to form. However, if the bond order is equal to 0, the molecule has no reason to want to form, so it won't form unless we force it to, which we're not going to necessarily in this class. But that's basically what the bond order equation is telling you. So if a question on the exam asks you, if a certain molecule will form, then you'll have to draw out its MO diagram and figure out the number of electrons in its bonding and the number of electrons in its antibonding, and figure out if it's stable. So a good, I'm just going to give you a little example here. Let's go ahead and go back to our helium example. So, sorry. Give me 2 seconds. So, in our helium example, this is a good one because it's going to give us kind of an error. If we have the number of electrons in our bonding MO, the number of our electrons in our bonding MO is going to be 2 for helium, minus the number of electrons in antibonding MO, which will be 2 as well. And if we do 2 minus 2, we have 0. If we take 1/2 of 0, it's not possible. It won't happen, okay? And that's kind of the equivalent of bond order being equal to 0. If it's equal to 0 or you form an error, then the molecule is stable as a single atom and will not form. And that makes sense for helium because helium is a noble gas and it has a complete octet in the sense of it's an exception to the octet rule. It only wants 2 electrons. So this one actually confirms us that helium won't form in that manner. We can set helium up in that manner and pretend that it does and say, hypothetically, if we have 4 electrons to give, will it bond? So as you can see, we drew out the diagram for helium earlier. We saw the possibility, but now we're going to say, does it actually work out? If we left it like that, does it happen? And the answer would be no, because it's equal to 0 or it's not possible. Mathematically, you can't divide 0 by 2. And that tells us that the molecule is stable as a single atom preferred to bonding to itself, so it won't form. But we can hypothetically say it would, but it doesn't mean it actually would. And that's why we use bond order, is to determine if it would or if it wouldn't. Does that make sense? Kind of. That's when we use this bond order equation. So there are 2 bond order equations, and this one is to check and see if it's actually possible for 2 atoms to bond together. Sometimes it is, sometimes it isn't. In helium, it's not very likely, just because it's a noble gas. So that kind of backs up that justification. Okay, so one little pattern is increase in bond order means an increase in the strength of bonds. Okay, so if we increase our bond order, we increase our strength of bonds. That we should already kind of be familiar with. The trend isn't going to change. It just applies it to here. So, as you can imagine, if you did one of these and its bond order was 5, compared to doing one and its bond order was 1, the one with the bond order of 5 would have a greater bond strength than the bond order of 1. Okay, so it really just kind of depends. You'd have to do the math to prove. On the exam, they might give you a question and say which of the following molecules has the highest bond order or has the strongest bonds, and then you'd have to solve for the bond order of each one of them, and then use this relationship to determine which one has a greater strength. And if I'm not mistaken, I have one of those. I have one of those problems on my exam review packet, so I do have an example for that. Okay. One more thing. I think this is the last part of chapter 11. Maybe. Yes. So it's just really homonuclear and heteronuclear. I just kind of throw these vocab in there just in case you do see it on the exam. Homonuclear is composed of 2 identical atoms. That would be a good example of H2 or your diatomics, right? Cl2, all of those. Those will be considered your diatomic, and they're also going to be homonuclear. And the only outer AOs interact to form your your MOs. So only your outer atomic orbitals interact to form your molecular orbitals. Okay, just your most outermost electrons, your outermost orbitals will form your new orbitals. However, heteronuclear, so diatomic molecules, meaning two or more molecules or atoms bonded together, have asymmetric MO diagrams because the AOs of the different atoms have unequal energies. So in the one I just showed you, hydrogen, it's very symmetrical, correct? The image that I showed you up here, it's very symmetrical, right? Those energies are all in the same area. They're all lined up. They're very pretty. However, if you start doing a heteronuclear and you do two different atoms, so maybe you have hydrogen and a chlorine bonded together, they're going to have different energies, right? They're not going to be the same atom. They'll have different energies. So their MO diagrams and their atomic orbitals will have different or unequal energies. Okay, so if you were to do it, it might be offset and you might have your 1s up here like that. You know, something like that where your image is not going to be perfectly symmetrical. And it does happen. But I mean, that's just, it's really more of a definition than an actual thing you'll have to apply. So if they say heteronuclear, no, they're talking about two different atoms. If they're talking about homonuclear, they're talking about two of the same. So I wouldn't really expect a problem that's specific to the definitions. Really, it'd just be in case they give you that word, in case they throw that word in some paragraph, now you know what it means, okay? All right. Any questions over just those definitions? Bond order, homonuclear, and heteronuclear? I believe this bond order here is the only new equation and the last equation that you should really be familiar with, which might be a relief to some of you that don't like the math part of chemistry, but I really do think this is the last important equation that you should know for this exam. So that might be a relief. Okay. So let's just go ahead and quickly review 12.1, and then that'll be it for today. Again, I'll probably end early, which is okay. I'm going to let y'all go enjoy your Thanksgiving break. But if you do have questions, you need to let me know at the end of this. And then you can also email me asking for specific things for the packet for my next sessions. But right now, I will have some practice problems for this material on my next packet. So don't worry about that. I will have them next time. Okay. So 12.1, an overview of physical states and phase changes. So potential energy is associated, I just want you to remember, associated with intermolecular forces and drawing molecules together. That's what potential energy is. Because when we have molecules, or not molecules, it should be atoms. Let me correct that. Hold on. So it really should be when we're drawing atoms together as molecules. That's what potential energy is, because that means we have bonds in between them, we have the potential to break them and create energy, or we have the potential to break them and put energy in, or we have the potential to form them and create energy. Okay, so that's what potential energy is associated with. I have seen some problems like that in the finals. Kinetic energy is associated with random motion and dispersion of molecules. We should already know that. If we have rotating things about bonds, if we have freely moving electrons, the dispersion of molecules, meaning we increase the energy of molecules and we can jump them from phases. Those are all considered kinetic energy. So random motion and dispersion of molecules. Again, the above interactions explain phase changes. Kinetic energy can explain phase changes, and that should be review, hopefully. This one's also important. Intramolecular bonding. Forces exist within a molecule and determine chemical behavior. So this is intramolecular bonding. As you can see, I've drawn H2O here. The intramolecular bonding, if you break those bonds, you change the chemical structure of water, and it's not the same anymore. However, intermolecular would be, that would be between that would be between water molecules. So the closer those water molecules are to each other, the less movement it has and the more solid it is. So intra is the bonds within an actual molecule. Inter is those between two different molecules. So let's just, for example, we know that water can help dissolve many things, right? So let's just take salt as an example. Water is a really good helper in dissolving salt. And we know this because we talked about water's polarity, and that helps it dissolve things. So it has a partial positive side and a partial negative side, right? So if I'm talking about the partial negative side of my oxygen or my water here, it's going to be, my partial negative side will be my oxygen side, and my partial positive side will be my hydrogen side, right? And that should all be from knowing how to do polarity, drawing polarity arrows, and all of that. So I should know that about my water in general. However, why water is really good at taking things apart is because of its polarity differences and because of its charge differences. So if I'm taking apart NaCl, I know that Na has a positive charge associated with it, and Cl has a negative charge associated with it, meaning that the partially positive side of my water will attract my chlorine because it's negative, and the partial negative side of my water will attract my sodium because it's partially positive, and it will end up yanking apart that compound. So NaCl will be torn apart from itself because sodium attracts to the negative side of water and chlorine will attract to the positive side of water. And the forces that are in between my sodium and my negative side of my water, or my oxygen side, that's considered an intermolecular force, okay? That's what an intermolecular force is, the forces that are interacting here. The intramolecular forces are the forces that are inside, right? The forces between my O and H. Intermolecular bonding deals with bonding between molecules, and intra bonding deals with bonding within a molecule. Exactly. Yeah, that's a perfect way of putting it. Mm-hmm. Okay. And oftentimes intermolecular bonding, the ones that occur in here between sodium and my negative side of my water, it's not forming an actual bond, right? It's kind of like a fake, it's an interaction, not a bond, okay? So that's also a good way of memorizing it. Intermolecular forces are more interactions, right? They're interacting, this positive is interacting with the negative. But intramolecular, that's an actual bond. We are forming a bond in our water, okay? So those are two good words to be familiar with. So yeah, okay. So forces exist within each molecule, determine the chemical behavior. This is another good example. I kind of did two here, but intermolecular bonding, forces exist between molecules and they determine physical behavior. So in this case, let's talk about physical behavior in regards to two different water molecules. We know that this oxygen has a negative charge, or a partial negative charge. This hydrogen has a partial positive charge, and that means they're going to be attracted to each other. Now, if we make that attraction stronger, those water molecules will get closer together and will become more solidified. We'll get ice. However, if we weaken our intermolecular forces, then our water will get farther apart, it'll be less attracted to each other, and we'll get something like water or even gas. Okay, so controlling those intermolecular forces controls our phases. It also helps us with dissociation, like in NaCl. So intermolecular, between molecules, intra, within each molecule. Okay. Rank the intermolecular forces of gas, liquid, and solid. We should know that. That was kind of a stupid thing to put on here. But really, we just need to know that gas is going to have the less intermolecular forces. Okay. Because I mean, I just said it. It wasn't a stupid thing to put on here. It was redundant to put on here. It was redundant. Yeah. So the weaker these intermolecular forces, the more gas it's going to be. So the gas has the weakest intermolecular, and the solid has the strongest intermolecular forces, which again, very redundant to what I just said, but maybe it will help you. So that's good. And then we have the relationship between temperature and kinetic energy. Again, that should be kind of redundant, a little bit familiar. If we increase temperature, we increase our kinetic energy. And remember, our kinetic energy is associated with tends to be associated with intermolecular bonding because that has to deal with phase changes, right? If we increase temperature, we're going to increase our phase change and our kinetic energy. And then just one last thing I decided to throw on here is this here, just because, and this is more, chapter 12, it's not necessarily a lot of new information. It's more of just kind of summarizing a lot of the stuff we've learned and making sure we all have like connected those dots. So if they use these terms, it's, this is what they mean. And I just don't want y'all to be confused. So I threw it on there just as like a little bit of a review before I go into exam material or like covering final exam material. So condensation, gas to liquid, vaporization, liquid to gas, freezing, liquid to solid, melting or fusion, solid to liquid, sublimation, solid to gas, and deposition, gas to solid. So that's all I have on my packet for today. I'm happy to answer questions for y'all, but if not, we'll end a little bit early. For those of you that are leaving, have a great Thanksgiving. If you're going home, be safe, travel safe, get home safe. But yeah, let me know if you have questions. Y'all too. See you in a week. Can I go through each page? What do you mean by that? Do you want me to like flip, like show you each page? Oh yeah. So it's a lot of writing. So if you can't read something, let me know. But all right, so that's it. Do you need me to go back to anything specifically? Yeah, of course. You too. Be safe. Okay. For those of you that are still in here, if you do have questions, feel free to email me and I will definitely either respond through email or answer them specifically in my next session. But if not, y'all have a great break and stay safe.